in acids and bases when we were studying acids and bases. So he's talking about, now remember, nitrogen compounds are basic. So he's talking about phenylamine. Now phenylamine is this thing. It's an amine with, so it's a benzene with NH2 group, and it's got these lone pairs. I've got ethylamine. Now ethylamine is a carbon chain with an amine, and I've got a third one which is 4-nitrophenylamine. So that's phenylamine with 4-nitro. So that one is phenylamine with 4-nitro, which means NO2. Now, the thing is, we have to figure out which one is the most basic and which one is the least basic. So we did study about, I mean, what is basic? Basic is something that accepts H+1. So it's all about who's going to attract H+1 the strongest. So here's another H+1, and here you have another H+1 ion. So who's going to attract the H+1 the strongest? The one that has the highest charge density on its lone pairs. And it has these lone pairs which attract H+1 ions. So out of all of these, which one has the greatest charge density? Now you did study that alkyl chains have electron donating effects. So there's going to be electron donating effect, which is why the charge density on this lone pair is going to be really high. So it's got a high charge density, and there's going to be more attraction for H+1 ions. So it's going to be the strongest base out of the three. Is this clear? Yes or no? Is this clear? Lubena, is this clear? Ethan, Ma?
Yep.
Okay, so just remember that alkyl chains have electron donating effect. What about the other two? Now, the other two are very similar, and we did discuss that the lone pairs kind of overlap. They had an electron, I mean, amine groups had electron donating effects. So what they would do is that they would overlap with benzene's electron cloud, and which is why the negative charge density would decrease. So this one is going to have a lower charge density, right? Is this also clear that the lone pairs, they mix up with the benzene electron cloud? Is this clear? And yes or no, is this clear?
Yes.
And if they mix up with the benzene's electron cloud, then what happens is they're not going to attract H+1 that strongly. And this one has an NO2 group. Now, we did study about NO2 groups that they're given in the data booklet as well. Just a second. So we did study about NO2 groups, that NO2 groups had electron withdrawing effect. So the net result would be there would be more electron withdrawing effect. So this one would be an even lower negative charge density. Because the NO2 group is pulling electrons from the other side as well. So not only are the lone pairs kind of overlapping with benzene electron cloud, but they're being dragged to the other side by the NO2 group as well. So this one would be the weakest base. Is this point clear? Clear, Kenny?
Yes, sir.
Okay, so just remember that everything depends on these lone pairs. If the lone pairs have really large negative charge density, they're going to attract the H+1 very strongly, and they're going to be very strong bases. And if the negative charge density is very less, which is in the case when it's bonded to benzene, and it's even lesser when it's bonded to, when the benzene has an NO2 group, that's even more electron withdrawing effect. So that one is the weakest. So that's all about this one.
Oh, sir.
Yes.
Why does phenylamine have a lower charge density?
I mean, this one,
Yeah.
because the lone pair mixes with benzene's electron cloud, it starts overlapping with it. So the lone pair gets, remember the benzene electron cloud was very distributed, right? So we did discuss this when we were talking about about 246 directing groups, right? That I told you that the lone pair mixes with benzene electron cloud. So the lone pair is not available over here at the moment. I mean, the negative charge over here would be lesser. Is this clear?
Oh, because the electron density goes into the benzene.
It goes into the benzene, that's why.
Yeah. Right.
Over here, the carbon chain electron density actually gets pushed onto the nitrogen atom. So over here, the negative charge density is even higher, right? I said then
Yep.
I mean, we can try and do this one. I'm sure we can try and do this one. You've got an arene, right? He's saying you're supposed to make this thing. So how do you make this thing? And there are 2 steps given. So, I mean, all you have to do is you have to do nitration and you've got to do bromination. So if you do, remember this thing, this methyl group is a 246 directing group. Remember, I told you that it pushes electron density. So the electron density becomes higher on the 2,4 positions, 2,6 positions, and also the rest of the electrons get pushed onto the carbon at the exact opposite end. So it's 246 directing. So if I add bromine, it's electrophilic substitution that would happen. I would need to add a catalyst as well. It would be FeBr3. And there's going to be methyl group. And a bromine might get attached to the carbon on the 2nd or the 4th position. So that is what we exactly wanted. Then we can do nitration as well. If you do nitration, for nitration, you would have to add concentrated nitric acid and sulfuric acid. And the temperature has to be kept at 55. And if you do that, so again, the methyl group is it's a 246 directing group. So the NO2 might get attached to the carbon on the 2nd one. That's the place that's left. Although there would be multiple other options that would be produced, but that is a possibility. And the last part, we already did that whenever you have a carbon chain, you oxidize it, KMNO4, acidified and reflux. So what happens is that the methyl group or the carbon chain turns into a carboxylic acid. So remember, we've already done this bromination of a 246 directing group, nitration of a 246 directing group, and we've done oxidation of arenes, which is that whenever benzene has a carbon chain, it eventually turns into a carboxylic acid. That's it. So give the systematic name of compound G. Now this is benzoic acid. Because it's a carboxylic acid with benzene. So this one is benzoic acid, and it's got 2 branches. One is at 2 and the other one is at 4. So alphabetically, bromine comes first, so it's 4-bromo and 2-nitro. Benzoic acid. And suggest reasons, we already did that, and so that's pretty much it. Now he's saying that let's try and do this one. So let's try and but we can ignore this one for now. Again, you've got another reaction where you've got a benzene, and he's adding AlCl3 catalyst. Now remember, we did alkylation as well. Alkylation was that I told you that if there was a carbon chain, and let me draw it like this. So alkylation was that if there was a carbon chain with hydrogen atoms and there was a Cl, the carbon over here has polarity. It's positive and the Cl is slightly or partially negative. The electron cloud from benzene are going to get attracted and the Cl is going to get repelled, but the polarization is not enough. So AlCl3 catalyst helps in polarizing the Cl or taking off the Cl from the other side. So halogenoalkanes would get attached. It's always the carbon that's bonded to Cl that's going to get attached to the benzene because that's the one that's polar. So if you look at this molecule is Cl with CH2, and then it's got two more CH2s, and then there is a COH. So remember, it's this carbon atom. This is the carbon atom that would be attracted to the benzene. So if you draw this molecule, the benzene, carbon. So it's going to be this carbon that's going to get attached to the benzene. So you have to be careful. This is acylation, Friedel-Crafts acylation and alkylation, which were also part of electrophilic substitution, which we already did. And there's going to be H and H. And at the end, there would be carboxylic acid. So is this clear, this thing? That halogenoalkanes, they get attracted to the benzene. Is this clear as well?
Yep.
So then, so we did some of those reactions and now we're saying write an equation for the formation of an electrophile from RC. Now RCl is the carbon chain. So basically what happens is, I mean, this is what's going on. How is the electrophile created? Because the Cl, I mean, the carbon chain, you had a carbon chain. The Cl, I mean, the aluminum chloride over here, AlCl3, pulls off the Cl atom and this turns into a carbocation. This is what's happening. So we have to write, I mean, they're asking for that there's RCl. And he's just calling that an alkyl chain with chlorine. So if you have an AlCl3, what the catalyst does is that the carbon chain becomes a carbocation and it becomes AlCl4 with a charge of -1. The aluminium pulls off the Cl from the other end. This not only happened with alkylation, it also happened with simple chlorination as well. Like if you were just chlorinating the molecule, the polarization was not enough. So you needed a catalyst. Like you add a chlorine molecule, the double bond electrons would repel the Cl would become negative, the Cl would become positive. The electrons would get repelled by the benzene electron cloud and the aluminium over here will pull off the Cl so that the chlorine becomes completely positive and gets attracted to the benzene electron cloud. So this is what we are showing over here. Is this clear?
Yes, sir.
And let me have the board is here. So then here's another one. Complete the mechanism for the reaction of benzene with the electrophile formed in B1. So now he's talking about the mechanism of the electrophile formed in B1. What's B1? I mean, this is B1. So he's talking about this one. This is the electrophile, the carbon chain, the carbocation. So remember we did the mechanisms for NO2 plus 1 and so on. And let me just so what would happen is once the carbocation is formed, the electron and the benzene are going to get attracted to it. The Cl has been taken off, and the carbocation chain will get attached to the benzene, and its electron would become, the benzene electron cloud would become electron deficient. And in the next step, the H would lose its electrons. It will give up its electrons so that the benzene electron cloud becomes complete again. And we did mechanisms like these. We did 2 of them. So I'll just quickly go over them to give this. Yeah, actually not on this one. So I'll just do a quick overview of all the mechanisms if this. So initially we talked about alkenes, and I told you that alkenes can polarize a molecule by itself because the electron density is really high. And we talked about benzene, that the electron density is not very high. It's like an alkene, but the electrons are much more distributed. So the polarization is not enough. So you need a catalyst. So we did these mechanisms where FeBr3 or FeCl3 catalyst would be needed so that the bromine molecule could be polarized further, and the Br-1 can be ripped off from one side, get attracted to Fe, and the Br positive could then go and bond with the electron cloud over here. Now we did all of these mechanisms. We did nitration, which was kind of similar. There's an NO2 plus 1 ion, and the NO2 takes away electrons from the benzene electron cloud, becomes positively charged, and then the H gives away its electrons, and NO2 replaces it. And this was alkylation, which was kind of similar, except that now it's the carbon chain, and it's always the carbon that's bonded to Cl that gets attached to the benzene. So we did all of this. So we can open another paper very quickly and do some more. So this one, you've got a molecule saying now this one can be synthesized using benzene as one of the starting materials. So he's trying to make this molecule out of benzene. So what you need to attach this thing to it, which basically means this must be the positive carbon that gets attached. I mean, if you can ignore this, it's going to get attached to the benzene. The electrons from benzene are going to get attached to this. So there must be a Cl. This is acylation. Like if we go back to the board, this was alkylation, and we did another one which was very similar, which was acylation. This one, that you can have a C double bond OCl, and the carbon could be highly positive, and the benzene electron cloud will get attracted to this carbon atom, and the Cl would eventually leave. And you would also need a catalyst in this case as well. An AlCl3 catalyst would work. The AlCl3 catalyst will rip off this Cl from the other end and pull it off and keep it with itself. So this is acylation. There's alkylation and then there's acylation. So this one, he's talking about acylation. So you got a C double bond O. So there must have been a Cl over here. So identify the other reagent. So it's going to be CH3, C double bond O, Cl. And the essential conditions for this would be AlCl3 catalyst. So this is also an example of electrophilic substitution. Now complete a table for each of the reagent to give the structural formula of one organic product formed. If there is no reaction, so you're saying chlorine gas at 10 degrees centigrade in the presence of UV light. If there's ultraviolet light, then what you're going to get is free radical substitution, which basically means that the H atoms will get substituted by Cl. So with UV light, the Cl always attacks the hydrogen atoms. So it might become CH2, CH2Cl, not the benzene. Chlorines get attached to benzene only when there's a catalyst involved, not otherwise. So under UV light, it's only these hydrogens that are going to get substituted. So free radical substitution would happen. And the name of the mechanism would be free radical substitution. Next one is nitric acid, sulfuric acid. Now, with nitric acid and sulfuric acid, what you're going to get is NO2 plus 1 electrophiles. And this group over here, a ketone group, is an electron withdrawing group. So that means the NO2 will get attached at position numbers 3 or 5. Remember, electron withdrawing groups, the benzene always get so this one. You have your 3,5 directing groups. Make sure, just hold on one second. So we'll quickly, where's the, so we'll quickly go through this thing, 2, 4, 6 directing groups and 3, 5. So I'm just going to give you a quick recap again. And I think it's hanging up. Just a second. So this one, remember 2, 4, 6 directing groups and 3, 5 directing groups. That where would the electrophiles go? So whenever you have a CO, C double bond O, that's going to direct it at the 3 position. And so any incoming electrophile will get positioned at the 3 position. So if we go back to our paper, which is this one, the NO2 will get attached on the 3rd carbon atom. 3 and 5 positions are kind of exactly the same. So For nitration, you need a mixture of nitric acid and sulfuric acid, and the temperature is around 50 centigrade. Is this clear? Yes or no? Is this clear, Ethan?
Sir, could you show the table again?
I mean, this is the table that we have over here. Just a second. That if you have a ketone group, that's an electron withdrawing group, and it's going to direct it at the third position. When you have an electron donating group, the electrons get pushed, and positions number 2, 4, and 6, the electron density increases over here. Vice versa, if you have an electron withdrawing group, where's the electron withdrawing group? So if you have a 3,5 directing group, which is an electron withdrawing group, then in the same positions, the electron density actually decreases because the electrons get withdrawn. Like if you have a ketone group, the electrons are going to get withdrawn from the benzene, and the electron density at position number 2 and 6 and 4 would be lesser. So electrophiles are not going to get attracted to those positions. Is this clear?
Yeah.
And the last one is with bromine water. What's going to happen when you react it with bromine water aqueous? Nothing's going to happen. Why? Because the benzene is not going to react unless there's a catalyst present. Alkenes can react without a catalyst, but not benzene. For benzene, you need a catalyst. There's only one benzene that actually reacts without catalyst, and that's a phenol. So if we just revise bromination, TK, we did all of that. Normal bromination, where's the normal bromination? For a normal bromination, you needed only bromine will not be able to react with a benzene because you would need a catalyst FeBr3. So that was electrophilic substitution with bromine. You needed a catalyst, but there were other types of benzenes which were way more active or activated. So for example, we did the electrophilic substitution of arenes. And if you added bromine, the bromine would get attached to position number 2 and 2, 4, or 6 because it's an electron donating group. But even in that case, you needed a catalyst. Then we did electrophilic substitution of phenols. And I told you that phenols and phenylamines were highly activated group because the lone pairs were mixing with the benzene electron cloud. So the electron density at the position number 2 and 4 and 6 were pretty high. So no catalyst was needed in this case. So bromination can happen, or polarization of the bromine molecule can happen by itself because the electron density is really high in the benzene, in a phenol or a phenylamine. So, and this was a test for phenols actually, that it could react with bromine to form a white precipitate. But Br2 aqueous only reacts with phenols or with phenylamines, not with this molecule. This is not a phenol. A phenol is a benzene with an OH. Is that also clear? Is this clear? Yes or no? So just remember that you should be aware of all these 4 electrophilic substitution reactions in detail, like which ones. You have bromination, you've got bromination chlorination, you've got nitration, you've got acylation and alkylation. And you have to remember that which ones are 2, 4, 6 directing and which ones are 3, 5 directing. The reactions of 3, 5 directing groups are slow or non-existent because they have an electron withdrawing tendency, which is why the electron density on the benzene decreases and the reaction doesn't really happen. And you've got electron donating groups, and in electron donating groups, the electron density actually increases, which is why the reactions are a bit faster. But with carbon chains, the electron density doesn't really increase that much. But with phenols or with amines, the electron density really increases a lot, which is why the reactions are really, in that case, the reactions are really fast. So you can do the reaction without a catalyst. Even the nitration reaction where you needed concentrated nitric acid and sulfuric acid, if it's If it's a phenol, then all you need is just dilute nitric acid or concentrated nitric acid. You don't even need you don't even need sulfuric acid for that, and the nitration would happen on its own. So just remember all the combinations that can happen. So with bromine aqueous, bromine water, no reaction. At the moment, there's not going to be any reaction because a catalyst is needed. You need FeBr3. It's not an activated benzene. If it had been phenol or phenylamine, then bromine water would have worked. You don't need a catalyst in that case. So now this one is nucleophilic addition. You already did this in AS. Carbon is positive, oxygen is partial negative. You have these CN- ions, which are your nucleophiles. They're going to get attracted to the carbon, which is positive, and the electrons are going to get repelled. This reaction has nothing to do with benzene. The oxygen over here would become -1. And the CN will get attached over here. And in the next step, the H+1 would come in and join, forming a cyanohydrin. So CN, CH3, and there's going to be OH here. And it would form a cyanohydrin. Now, he's saying, I just wanted to stick with benzene for a second. So let's try and do this. He's saying it can be used as a starting material in a two-step reaction. So you have to make this thing. What you can do is you need to turn this into an alkene. So what you can do is, this is a ketone. Ketones can be reduced back to secondary alcohol. So you can do that. Reduce it back to a secondary alcohol. So it will turn into an OH with an H and a CH3. And then do dehydration. How do you reduce it? You reduce it with NaBH4, which is a reducing agent. And the H and the OH could be lost. So that's dehydration. And if you dehydrate it, it will turn into an alkene. How do you dehydrate it? You heat it with Al2O3 plus heat. Or you use concentrated sulfuric acid, pass it through it. That's a dehydrating agent as well. So let's try and see if there's. So this one is about nitrogen compounds. So we're gonna we'll continue next week with nitrogen compounds. Those are the ones that are left. TK, we've covered most of organic. We did acids and bases previously as well, so I'll revise that. We did one question on acids and bases, but the only thing that's left is nitrogen compounds and polymers, polymers are the same as what you did in O-levels. So we'll continue with that in the next week. Next week we'll probably be done with organic, TK, and we'll be doing past paper questions only. So TK, let's talk next week then. Okay, everyone.
Thank you.
Take care, Hafiz.